bridges in today's society have pushed at the limits of engineering and design, to the point where we can put a bridge almost anywhere. We've got bridges that span rivers, that traverse mountain ranges, bridges over oceans, that connect countries, soar above jungles and more. Sometimes, they seem almost timeless while being transcendent. Let's face it. We couldn't live without bridges. We have been assigned to the task of investigating different bridge types and the strength each of their elements provide, under different internal forces. The objective of this analysis was to design and construct the lightest bridge, capable of supporting the greatest load in order to understand basic principles of engineering. In this project, you are required to work in a group to design, build and load a spaghetti bridge of any type until it fails. While constructing the bridge, there were parameters that were required. These included: the entire bridge must be constructed solely of spaghetti and superglue. Only Selleys quick superglue shall be used as a spaghetti bonding material. The bridge will be weighed before testing. The bridge needs to cover a 350 mm span. There also must be a loading plate, and eye bolt must be able to be easily added to your bridge post-construction. This will be used to attach the loading arm to your structure. The loading plate shall be located at the bottom surface of the midspan of the bridge. So for following these parameters, we have constructed and tested 2 of the required bridges for this report analysis. When developing these bridges, we looked at truss bridges. A truss bridge is a load-bearing superstructure and is composed of a truss, which is a structure of connected elements usually forming triangular units. The connected elements may be stressed from tension, compression, or sometimes both in response to dynamic loads. When looking for a simplistic design for our bridge, it was decided that the truss bridge suited most, and that a Pratt truss bridge would be best for our design. Bridge 1 and 2 for this project was designed incorporating components of a Pratt truss bridge. The basic types of truss bridges simple designs date back to 19th and early 20th century engineers. The Pratt truss is a very common type, but has many variations. It still incorporates the truss bridge square, rhombus shape looking from the width side view of the bridge. This was done to keep her strong and stable and therefore well suited for the assignment at hand. The basic identifying features are the diagonal web members which form a V-shape. The center section commonly has crossing diagonal members. Additional counterbraces may be used and can make identification more difficult. However, the Pratt and its variations are the most common type of all trusses. This is most likely due to truss bridges being economical to construct because it uses materials efficiently. In the first design stage, we didn't know the best way of constructing a spaghetti bridge. It was decided that once we worked out the basic conceptual design, which was after conducting research on bridge types, and due to lecture and tutorial learning from Structures 1, Learnings of Truss Construction, it was quickly decided on the truss bridge. The group did a basic SketchUp and decided to move forward with a hands-on approach to learning and really just see how the first bridge construction was conducted. Here is some videos of the construction process for Bridge 1.
Late night constructions with the pasta. Trusses.
Although we had become skeptical about the overall strength of our design due to the extensive number of joints. As shown in the photos and videos prior, the test of the bridge revealed a critical failure at 7.5 kilograms and a breaking point at the center joint of the bottom chord. The overall construction and testing of this bridge provided us with a significant amount of information on which elements of our final bridge required attention and improvement. On the secondary bridge design, our main objective was to reduce the number of members in the structure. We decided that the initial design was suitable, however the construction of the truss would be altered to incorporate only 3 large triangles. A firm understanding of these forces was developed, the most at-risk members of the bridge were identified and taken into account during the construction of the final bridge. The calculations and findings through the software analysis allowed for the new truss bridge to be designed to withstand more distributed load and improve the performance of our design from the first attempt. We shall go straight to testing of bridge 2. This is due to the construction phase being too similar between bridges 1 and 2. The results of the structural integrity of the second bridge were expected to exceed those of the original. When tested to failure, however, our secondary bridge failed at a surprising load-bearing capacity of only 7.5 kilograms. It also weighed heavier than the first bridge. This assignment has developed a firm understanding of the structural elements of a Pratt truss bridge and structural testing techniques, and this knowledge can be taken and applied to real-world scenarios. The construction and testing of the 2 spaghetti bridges aided in the further comprehension of 2 important factors to consider in bridge construction. 1. The importance of well-designed structures and the limitations of the components that may lead to the failure of the construction. And 2. The likelihood of defective materials and the potential outcomes resulting from the failure of these defective materials. Thanks for watching.